Okay. Okay, so I'm going to repeat myself. I have two situations. I'm compressing, so I'm giving the spring maximum X or maximum displacement. What is maximum displacement? It is amplitude. And when I'm stretching, I am also giving it maximum X or amplitude, the maximum amplitude or the maximum displacement. What happens when I have my maximum X? My PE becomes maximum, my KE becomes zero. Why? Because when I compress my spring, I am holding it from moving, right? My KE is zero because V is equal to zero. Why is PE maximum? Remember, your equation for PE is equal to 1 over 2 kx squared. If this guy is the maximum displacement, your PE is maximum as well. So this guy becomes PE max, right? So when PE maximum happens, KE is equal to 0. Okay, let me write that down here as well. So this is maximum. PE also becomes maximum. When I stretch it, I am also giving it maximum X. PE is also maximum. KE is also equal to 0 at this point when I'm stretching it and when it is compressed. Okay, so now kita bayangkan, oh terkejut aku. When we are stretching it and then I release my spring, what happens? It goes back to equilibrium. Ataupun when I compress it, I release it, it goes back to equilibrium. So in this case, kita tengok kat compression punya dulu. Release, dia akan go back to equilibrium. It goes back to this point. What happens at equilibrium? Your X becomes 0. Your displacement becomes 0. What happens? Your PE becomes 0. Because of this equation, 1 over 2 kx squared. When your X is equal to 0, PE is equal to 0. What happens to your KE? KE becomes the maximum. So at the equilibrium, you will get your maximum velocity from this equation. 1 over 2 mv max squared. Macam mana dia boleh jadi maximum? Remember, our E is constant. When PE is equal to 0, sit up. When PE is equal to 0, your KE has to be the maximum that it can be so that the E can maintain to be a constant. Sama juga the case when your PE is the maximum. Your KE has to become 0. KE becomes 0, okay, because E is constant. So that is the maximum that it can go. PE maximum and KE maximum. Is PE maximum equal to KE maximum? Is the value the same? Is it? Is the value the same? Tengok balik equation ni. Is it the same?
Yes.
Yes. E is constant. When PE is 0, you get KE max. E is constant. When PE max, KE is 0, which means that this guy over here is equal to PE max. Okay, so I wrote it here dulu. Nanti kita akan come back to this equation, to this relation. Okay. So I told you PE maximum at compression or stretch, right? And this is what happens. KE becomes 0. And then at equilibrium, this is when you are reaching equilibrium. KE becomes maximum, PE becomes 0. And then when you stretch it, PE becomes maximum and KE becomes 0. Now, with that in mind, let's look at the equation. Okay, balik. Tengok balik equation dia. Bukan, not this one. Okay, so this one. So total energy is equal to kinetic plus PE or UE or US. I don't remember what it's called. U lah. Okay, so let's just use PE here. KE plus PE equals to E. Okay, when KE is 0, maksudnya yang ni jadi 0. Sorry, when PE becomes 0, this guy becomes a 0. This guy becomes the maximum. E equals to 1 over 2 mv max squared. Okay, sama juga when my mv is equal to 0, when my KE is equal to 0, this guy becomes the maximum. What is the maximum displacement? It is amplitude. So your equation becomes 1 over 2 Ka squared because that is the maximum amplitude. Okay, Vmax, you just label it as Vmax lah. Maximum displacement, label it as A, amplitude, for a simple harmonic motion spring mass system. Okay, now let's look at this graph. When my total energy is constant, okay, so ni another representation lah, dia punya value. Let's say total energy is 100%. Memang pun lah. Total energy is 100%. If my potential energy is 20%, my KE has to be 80% because the total needs to be constant. The total needs to be 100%. If my KE is, kita buat value lain lah. Kita cakap KE is 40%. So now it's 40%. What should potential energy be? It should be 60.
60.
Yes, because we always want to make sure that our E stays the same. It stays constant. Again, kalau PE turun, KE kena naik. Kalau KE turun, PE kena naik, and vice versa. Okay, so now that we have this equation, 1 equation, this 2 equation, and 3. Okay, what happens now? Of course, substitution happens. I told you, PE maximum punya value is equal to KE maximum punya value, right? So now we know the equation for PE maximum is 1 over 2 KA squared and the KE maximum is 1 over 2 MV max squared. Now I can rewrite this as V max. Kita boleh potong ni. And then KM, right? And I want to solve for this K over M. Then I have A squared and I want to square the whole thing. When I square the whole thing, I can get rid of the square for the A. So this becomes KMA. So that is my V maximum. When does V maximum happen? It happens only at the equilibrium point. So this guy happens only at equilibrium.
What's dragon?
Or
What's dragon?
when
Please.
X equals to 0.
Please.
Tak boleh lah.
The baby.
Main benda lain. Okay? Because this is when PE is equal to 0. Maksudnya KE kena maximum. Okay? Right. Okay, so we have another form of the equation. Lagu tu okay je kan? Macam lagu hotel pula. Okay, so you know that the general equation for your total energy is 1 over 2 mv squared plus 1 over 2 kx squared. Sekejap Okay, I'm back. Okay, so we know that this equation is the total energy, which is KE plus PE. And I told you E is constant and E punya value akan jadi PE max or boleh jadi KE max because this happens when KE equals 0. This happens when PE equals to 0. Right, so PE maximum, the equation for this guy is 1 over 2. Let me write that down here. PE max is 1 over 2 KA squared. So here dia nak cakap, because we know what the total energy is, if we know the amplitude, they equate this equation, 1 over 2 KA squared, with this guy over here. So now you can find out what is the velocity at random points. Tadi, okay, what is the difference between V and V max? Let's look at it. V max happens only at equilibrium when your PE is 0. What if your PE is not 0? Okay, when does that happen? So I have a spring. This is max A, max minus A. I shouldn't say max A minus A. I should say A and minus A je. Okay, so this is equilibrium. And we know what happens here. This is PE0, KE max. Okay, I'm going to repeat myself sampai korang ingat. Then PE max, KE 0. Okay, tu kita cari V max daripada here, pada equilibrium. So now, when do we use V? When I stop, when the spring is oscillating, right? And then I take a picture, tengok-tengok dia stop dekat tengah-tengah sini. Dia tengah stop kat sini lah. The displacement is over here. I don't know what happens there. I don't know what the amplitude is because I need a ruler to measure. I don't know what the velocity is there. So how do I find the velocity at this random point that is not the equilibrium or the maximum? I use this equation. This is when I use V equals to Km A squared minus, no ni salah ni. Dalam buku dia macam ni. Okay, this is the equation that you use when your spring berhenti at random points and you want to know what is the velocity there. Tadi lah dia berhenti, maksudnya kita tangkap gambar that at that particular point, what is the velocity? This is the equation that you should use. Okay. Faham ke? Is that okay?
Tapi kalau kita nak cari satu velocity tu kan macam tadi kan, kalau spring tu ada kat tengah-tengah di antara PE max dengan KE max tu kan, kita kena ikut equation bawah ni kan. Tapi kalau kita pakai equation atas ni boleh je kan, cuma
boleh?
rabut lah.
Ni rearranging je. Rearrange
Okay.
dapat yang ni. Betul, boleh pakai dua-dua. If you like the this equation better, use it. Ni pun boleh. Basically, it's just rearranging of the first equation over here. Equation number 1, rearrange jadi equation number 2. Okay. Right, so now, tadi tu spring mass system. Okay, let me write down what we have learned for a spring mass system. Okay, let's insert a new slide. Okay, for a spring mass system, kita dah belajar. Okay, spring mass ni apa? It's a spring and it has a mass. Okay, kita belajar when we stretch, we go to the maximum amplitude, we get PE max, we get KE 0. This is equal to 1/2 KA squared. Sama juga when I compress, negative A, PE max, KE 0, my energy is KA squared. Equilibrium point, PE 0, KE max, my equation is 1/2 mv max squared. This is the energy. Okay, punya equation. So this is energy punya equation. Okay, the generic equation for the energy, right? Yang ni jadual The generic equation for energy is equal to 1/2 mv squared plus 1/2 kx squared. This is assuming you don't know, you are at a particular displacement that is random, it's not at the maximum, it's not at the equilibrium. So this is when you use the equation. And from this equation, you can, because we know that energy is always constant, we can equate this to 1/2 Ka squared, because energy is constant. I can also equate this equation with 1/2 mv max squared equals to this guy up here lah. Okay, so from that equation, I get my two other equations, right? So I get my Vmax equals to apa tadi? Km square root A, and V equals to Km A squared minus X squared dalam kurungan square root. So perbezaan antara equation V, sorry, this is not Vmax. This is V, So perbezaan antara dua equation ni ialah ada minus X squared. We have the X squared minus X squared over here. Okay, sebab apa? Yang ni sama je sebenarnya, macam ni. Dia sama je, cuma V max terus pakai A squared. Kalau V, A squared minus X squared. Okay. Okay, apa lagi? What have we learned so far for the spring mass system? Okay, so the angular frequency is this guy. Omega equals to square root of K over M. Macam mana kita derive? Kita derive from F equals to MA. A equals to minus omega squared X. We use these three equations together and we got this, okay? Then from here, you can get your T and your frequency from omega equals to 2 pi F. Okay, so that is your mass spring system. Now we are going into simple pendulum. Okay, I'm going to give everyone 7-minute break before we go into simple pendulum. Please come back at 3:08. Okay?
Doctor,
Yep.
for the equation just now, half kx squared plus half mb squared equals half ka squared. Can the one where x is at any point? Yeah. Can we equate it? If let's say we don't want to equate the final as at the maximum amplitude, maximum displacement, then can we equate it such that the kinetic energy is maximum? That means it's at equilibrium.
You want to equate this equation with KE maximum. Is that what you're saying?
Because the situation in the buku, they say first it's at some random point and then it goes to the amplitude or the maximum displacement. That's the final. But then let's say the final situation, we make it as it returns to the equilibrium.
Which page are you talking about? Boleh bagi tahu tak, Bel? Which page is it, Bel?
111.
Okay, so here you are saying that it stretches and then it moves. Saya tak faham. Macam mana? What was the issue, Bel?
Okay, and Dr. macam ni. Here kan, half kx squared plus half mv squared equals half ka squared. Kan,
Yes.
Doctor? That means the initial situation is at some random point. You just take the picture. Kan?
Yes.
And then for the final situation, after the change in energy, we take it as the ball reaches, or the spring reaches the maximum displacement or reaches the amplitude. Kan, Doctor? But can the final situation be when the spring reaches the equilibrium back? That means PE is 0 and then KE max. So the equation equals to half mv max squared.
Boleh? This is what I wrote. Half plus 1/2 kx squared. This is also 1/2 mv squared plus 1/2 kx squared. Boleh? Is that what you're saying? Because E is constant. Betul ke tu? Am I answering your question, Bel? Aish, that's so bad. Okay, any other question? Bel dah hilang.
Doctor,
Yep.
Doctor, does it mean that when we want to find because the energy is constant, so the energy is conserved in the closed system, so the energy initial is equal to the final energy.
Yes.
So when we want to find the V, we use the equation that is the lower one, and then when we want to find the maximum velocity, we use the other.
Yes. Yes.
Also, we don't need to see the position, we just use the equation.
No need to change the position, just use the equation. Yang tu ke Mazen cakap?
Yes. Do
Ah,
we need to refer to the figure?
No. Kalau soalan dia boleh cakap macam ni. What is the maximum velocity when it reaches the equilibrium? Then you use the Vmax. But sometimes they don't say what is the maximum velocity. They say what is the velocity at the equilibrium position. So now you have to figure it out. Should you use a Vmax or V? And remember, your Vmax happens at the equilibrium. So you have to use Vmax punya equation. Faham tak? Okay.
Faham.
Okay.
So doctor, how about the question to find the V?
How about the equation to find the V?
The question, just like the question.
Okay. Okay, so tadi mula-mula saya cakap kat Mazen, equation dia, soalan dia cakap, what is the velocity at x equals to 0? And we know that x equals to 0 when the system is in a motion, KE is maximum there, right? Okay, KE is maximum. We already wrote that there. So kita pakai equation yang ni, Vmax. Terus pakai. We already know dekat equilibrium, KE is maximum. So Vmax. Okay, so what is the example of question kalau kita nak pakai equation V ni, betul tak? Okay, so let's say I say, what is the velocity? What is the velocity of a SHM spring mass system? Okay, spring mass system when the spring reaches, okay, when the spring is at x equals to 2 centimeter, and then they will provide you the amplitude lah, ataupun they show you the diagram that shows the amplitude. So now you have your x, put that inside your equation, you will know your amplitude, put that into your equation. That is how you find the V. Okay, so x is at random point lah. So it can be 2, it can be 1, it can be 0.5, doesn't matter. As long as it is not at the maximum displacement or it is not at the equilibrium, then you use this equation.
Alright, faham. Thank you,
Okay.
doctor.
Use, let me besarkan ni. Use when not at x equals to 0 or x is maximum or A. Okay, this is when you use this equation V. Okay.
Betul.
Apa dia?
Kalau kita tengok sekarang ni kan,
Mm-hmm.
E ialah 1/2 KA kuasa 2 kan?
E,
Okay. So when it reaches to the daya keupayaan paling tinggi kan, bila dia 1/2 kx max tu, automatically half mv square tu akan jadi kosong, right? Alright. So basically x tu samalah dengan A, right?
X tu sama dengan A. Kalau awak sampai tempat maximum displacement, this guy, maximum displacement becomes A. 0. Sama, 1/2 KA squared, 1/2 KX squared. Betul?
Alright. So if so okay, nampak. Thank you.
So bila PE is 0, this guy becomes 0, this guy becomes mv squared, 1/2 mv max squared. Sama. When this guy is 0, this guy becomes PE max, this guy becomes KA squared, 1/2 KA squared. Sama. So this holds for any situation. Sekarang ni nak pakai equation mana satu ni depending on your soalan. Soalan tu kasih awak amplitude ke, kasih Vmax ke, apa yang dia kasih. So depending on the question, pick your most suitable equation to use lah. Okay, padam balik. Okay. Right, kita dah habis masa untuk rehat ke? Alright, ada orang?
Doktor,
Yeah.
Sorry doktor, tadi saya terkeluar masa doktor sedang explain.
Okay.
Tadi kan, for doctor's explanation, is it the same as Neon's explanation yang doktor beri Neon?
Neon? Oh, Meon. Apa ni Meon? Yes, sama.
Okay, thank you doctor. So that means we can play around with the equation kan doctor, based on the situation they give us.
Yes, correct.
Thank you doctor.
Alright. Mungkin dah habis masa untuk rehat. Ke korang nak rehat lagi? I'm okay. Boleh sambung Saya sambung tau.
Sambung.
Boleh sambung.
Okay, so now kita dah habis cakap pasal spring mesh system. Now we are talking about the second SHM system, which is a simple pendulum. Okay, so simple pendulum, of course, equation dia akan lain sikit lah. Okay, so let's take a look at this guy right here. Let me besarkan dulu. Okay, so now we are doing our free body diagram. So we have our center of mass, we have our mg, and then we have our tension because we have a string. Okay, this is our center of the string, which means that if I'm looking at from the dinding, I also have tension here, but I don't care about that. I just want to know about the ball. Okay, so now if I were to resolve the mg, okay, I need to know the angle. So I have an angle over here as theta, and if I look down here, theta ni besar sangat pula. If I look down here, this shape is exactly the same as this guy over here, which means that my theta is the same. Okay, itu baru pasal theta. Okay, so theta up here and theta down here is the same. We have concluded that. So now I can resolve it, and resolve if this is theta, this becomes mg cosine theta, and this guy becomes mg sine theta. Okay, so now I want to say this is my this is my y-axis, because I can choose whatever axis that I like as long as they are perpendicular. This is my x-axis. Okay, so now that is my x-axis and y-axis. So I want to do my equation now. So since my ball is not bouncing up and down, I can say that it is in equilibrium in the y-axis, right? So now my equation becomes Fy equals to 0. Am I recording? Yes, Fy equals to 0. And what is in my free body diagram? This is my condition. What is in my free body diagram punya? From this figure, I can see that I have positive t because it's going upward. And I have my mg cosine theta minus. Okay. Okay, tak boleh ke tepi dah. Okay, so that means that whatever it is, so t is equal to mg cosine theta lah. Okay lah, tak kisahlah because it is in equilibrium. So now I want to look at my x-axis pula. Okay, so my equation for x-axis. Cuba tempat lah. How do I do this? Sekejap alihkan dulu sekejap period ni. Kesian dia. Tak apalah. Bersabarlah dulu. Okay, so my fx now, net in the fx, I know there is some sort of acceleration going on because it is moving repetitively, right? There is motion. So let's say it's not 0, memang tak 0 lah because ada acceleration. And let's say it's going to MA, and this guy becomes minus mg sine theta. Okay, because kenapa dia negatif? Sebab dia ke kiri. Saya nak cakap positive to the right. Okay, so we have come this far. Now, before that, saya nak kena tunjuk gambar triangle. Okay, so look at this guy over here. Okay, this guy. I need a different pen. Let's use green. So look at this triangle here. Okay, so this is S, the hypotenuse is L, and this is theta. So my sine theta is opposite over hypotenuse, right? So it's S over L. So I can substitute this S over L into this equation. So now it becomes minus mg apa tadi? S over L. Okay. Lepas tu, and I know for a simple harmonic motion, we have derived earlier that F equals to MA, where A is equal to minus omega squared X, right? So this equation, when I equate these two together, where do I equate it? That's what tempat. Let me use black now. When I equate these two together, I get minus mg S over L equals to minus m omega squared x. Now, S and X are the same thing. They are both displacement, right? Look at this guy. This is the displacement of the pendulum. So S and X are the same thing basically. Cuma term je lain. So I can cancel that out. And I can cancel my mass out. I can also cancel my negative sign. What am I left with? I'm left with, tak cukup tempat, G over L, sorry, G over L kecil pula. G over L equals to omega squared. So omega equals to G over L square root. Okay, whatever that is, it's here lah. Ta-da! So I got it. Okay, so G over L equals to omega squared, which gives me this guy over here. So this is the angular frequency for a simple pendulum. Okay. Tadi spring mass system. Omega dia square root of K over M. This is spring mass system. Simple pendulum, omega dia G over L. Okay. Alright, and as usual, when you have omega, you can convert it to 2 pi F. You can convert it to frequency. You can also convert it to 2 pi over T. You can solve for your T and your F. Just rearrange the equation. Okay. So you just need to know omega equals to square root G over L for this guy. Okay, yang lain tu boleh abaikan, tak membantu explanation. Alright, so the physical pendulum tu kita derive equation dia for a generic system. Generic and simple pendulum. What if we have a system that is not as generic and it's not a ball? Let's say I have this half a cylinder where the axis of rotation, sorry, this is the center of mass, mg, and this is my axis of rotation. So it is swinging back and forth. So that is also a simple harmonic motion, right? It is repetitive over the same path. But the shape of this guy is weird. So obviously the approximation will not hold sebab kita punya approximation was for a simple pendulum that was a ball, right? So what if it's not a ball? So this is where you use this equation, which is not in your book. I'm just showing it to you. So the equation ada I, moment of inertia. Remember, when we have like weird shapes, we can use the moment of inertia to approximate. So you can still calculate for the simple harmonic motion for weird things that are in oscillation, provided that you know what is the I, the moment of inertia, right? So this is not in your book. I'm just telling you as an exposure. So you can actually solve it in case nak sambung PhD ke. So adalah, okay, the mathematical expression for that. All right, so damped oscillation. Have we covered this before? Cetak kan? Okay, so damped oscillation. What is the difference compared to a normal oscillation? So oscillation yang biasa. Oscillation that is normal. You have repetitive motion over the same path. Okay, it does not change in amplitude because you basically oscillate from negative A to A, negative A to A, right, over the same path. So you go from negative A to A. This is your normal oscillation. Damped oscillation, your A, right, this is your A, negative A to A, it decreases over time. It becomes smaller and smaller and smaller. So that is damped oscillation. What do you need to know about damped oscillation? You need to know that the amplitude reduces over time. Damped oscillation reduces the amplitude over time. Do you need to know underdamped, critically damped, or overdamped? No, you don't have to. You just need to know what is the difference between a normal oscillation versus a damped oscillation. Okay, so dia boleh tanya macam ni. What is a damped oscillator? A damped oscillator is an oscillator that that oscillates with reduced amplitude over time. Boleh jawab macam tu. As long as the keywords are there, reduced time of amplitude, reduced amplitude over time. Ada keyword dia, settle. Okay. So this is a example, tak payahlah. What is next? Okay. Okay, so let's continue. Saya cakap problems nanti saya akan cover in a different lecture. Saya akan combine semua sekali so that we can speed up. Alright, so now we are going into mechanical waves. Okay, yeah. We're doing mechanical waves and this is like a demonstration lah. Okay, saya tengah ice breaking or tengah team building lah. I push this guy. Okay, I push because I'm feeling mean. I push this guy and this guy said, okay, I want to push the next guy. I want to push the next guy. And the next guy pushes the next guy. The next guy pushes the next guy. What is happening here? The push energy travels. But are we traveling? Am I traveling as a person? Am I like moving? No, I'm not moving. I'm just pushing. And then I'm just there, right? And basically the particle, I am the particle here. I'm not moving. But what moves? The energy moves. So mechanical waves, the particles do not move per se. They do not move like forward, but the energy is traveling. They transfer the energy forward. Okay, so let's see the next example. These are a bunch of particles. I push this red thing and I supply the energy. What happens? The energy travels. The energy travels, but the particles are like going sikit je, going manja. So they oscillate at a certain place. They don't move forward, they oscillate. They do a repetitive motion as they transfer the energy forward. So that is a mechanical wave. Sama juga sini, the particles in this string, they do not move. They only oscillate up and down, right? They move up and down lah basically, or left or right. Kat sini left or right. Yang ni up and down, but at a certain place je. But what travels to the end? The energy travels. Okay, so again, the particles of the medium does not exactly move. Okay, they oscillate at a certain place as they travel, as the energy travels forward. Okay, so that is a mechanical wave. So a traveling pulse propagates the disturbance along its path and transfers the energy from one point to another. So traveling pulse is also a type of mechanical wave. It's just a different name. So unless there is a disturbance, there is no energy to be transferred. Kalau saya tak tolak, tak ada benda yang nak ditransferkan. So there must be some sort of disturbance. Disturbance so that we have energy to propagate. Propagate, is that a word that you know? So that energy to travel lah. Okay, propagate ni travel lah basically. But it is always used for light, for energy. So propagate means moving lah, moving. Propagate means moving. Okay, disturbance, you have to provide the disturbance, you have to provide the push. You have to provide the push so that there is energy to be propagated. So that there is energy to be transferred. Okay, macam tu. Okay. So here is another type of mechanical wave happening. So kita dah cakap pasal particle ni only moves at a certain place je. Dia oscillate manja-manja macam tu, kiri kanan. Sama juga if I use the, what do you call this? Apa benda lah ni? Apa?
Tuning fork, doctor.
Oh, tuning fork. Okay. So I use the tuning fork, ting, right? So I can feel some sort of vibration going on. But in reality, the air does not move. Ada ke bila saya tekan ting, ada tak angin tiba-tiba? There's no wind. So maksudnya the air does not move. Kalau ada wind, macam cerita hantu lah pula kan. So when I do ting, the air does not move, but I can sense some sort of vibration going on. The air does not move, but the energy travels. So that the vibration that you are feeling somewhat is the energy that is traveling, not the air. The air is just oscillating about its place, right? So that is mechanical energy. Mechanical energy, but mechanical wave, right? Okay, again, I'm going to repeat myself. Wave is a type of oscillation, but it moves. What moves? The energy moves. The particles that transmit this energy does not move, okay? So it oscillates. So kita ada dua komponen kat sini, oscillation and moving. Kalau move, energy sahaja. Oscillation, particles of the medium. Okay, I hope that's clear. Next. All waves result from a disturbance. The disturbance are propagated in some medium. Okay, mechanical wave is a transfer of energy without the accompanying transfer of matter. Maksudnya matter tak bergerak. Okay, next. Okay, sama juga, another example. Observe the yellow dot. The yellow dot is your particle. The energy, right, it moves from, dia pergi sini, dia pergi ke kanan. That is not helpful. So the energy is to the right. But your dot, the yellow dot is just there. It just oscillates at its position repetitively, right? So GIFs are very helpful to demonstrate this. Baik. Okay, so we have two types of waves. One is called transverse. This is our first one. Transverse goes up and down. What goes up and down? The particle. The energy goes, the energy moves forward. So this is for a transverse wave, the particle goes up and down, the energy moves forward, which means that the particle and the energy are perpendicular to each other. So when the particle motion is perpendicular to the energy, this is called a transverse wave. An example of this is this spring. The spring goes up and down, okay, it goes up and down, but this guy, this lump, the disturbance travels forward. Okay, you can see when you use a spring, you do like this. Lemak tak nampak pula tangan saya, dia jadi hantu. Okay, dia macam tu kan. Kita buat macam tu, kita goyang-goyangkan spring tu. The energy travels, but sebenarnya the particle of the spring goes up and down. Okay, kalau dia bergerak sekali, then the spring is not in your hand dah lah. Dia dah pergi merata, dah jadi snake. So that's not possible, that's not logic lah. Okay, so that is the first one. The particle moves up and down, the energy goes forward. They are perpendicular to each other, so we call this a transverse wave. Okay, next one is longitudinal wave. Longitudinal wave. Okay, so the particle, how did I write this one just now? Okay, number 2. So number 2 is longitudinal wave. The particle goes left and right, and the energy goes forward. So these two guys, particle and the energy, are in parallel. So this is called a longitudinal wave. An example of this is this spring. I tolak ke depan, tolak ke depan, tolak ke depan, right? So what happens is the particles goes back and goes depan, belakang, depan, belakang, depan, belakang, and the energy goes forward. So they are parallel. They are in the same axis. This is called a longitudinal wave. Okay. So kalau kita nak tengok tadi kan transverse wave. Oops. So for a transverse wave, kita tengok benda Allah ni yang bergerak. The bump, it moves forward, right? For a longitudinal wave, we notice that the compression is what travels. So the compression, pemampatan tu lah yang bergerak. Kita nampak dia bergerak sepanjang spring. So that is the energy moving. Okay? All right. Next one. Any questions so far? Is everyone okay? Okay, are you asleep?
Okay.
Okay. Yes, ada soalan? Tak ada? Okay, so let's move on. Okay, previously we've learned that for a spring, we have the A, the maximum amplitude, and it was oscillating from A to negative A to negative A. Now here we have a mechanical wave happening. Mechanical wave, or just wave je lah. We have a wave going on here from our string where it is transmitting energy forward, but the particles goes up and down. The particles motion up and down is the amplitude. So that is the displacement over here. So how do I label this? If this was my axis, kalau kita nak samakan dengan plot simple harmonic motion from previous subchapter, right? This would be our A, this would be our minus A. So this is the amplitude, right? And we said that one cycle, right? We said one cycle is one period, happens over one period. And this is also equal to, one cycle is one period, and then it repeats itself, right? That is for the oscillation. Untuk mechanical wave, kita ada oscillation juga, right? So it means that we also repeat ourselves. So when do we repeat this? Okay, we repeat ourselves over here. If I cross it here, I can say that, okay, this is identical to this section. I am repeating myself. There is oscillation going on. I'm also transmitting energy because I can see that something is moving, right? So this is, I'm just trying to relate this string back to your plot hari tu, plot yang SHM tu. So this is A, this is your x-axis, this is your y-axis, which is usually your displacement. Okay, displacement. Let's write displacement. Meters. Okay. So when it starts repeating itself, that means it has reached one cycle, right? So this one cycle means one period. This is 2 period, and then so on, 3 period, and so on. Okay, so this is if the x-axis is in time, seconds, right? How do I relate this to wavelength? This is a new term for you. One cycle or one period is also equal to one wavelength. Okay, one wavelength. So if I were to plot it, if I were to plot the displacement over wavelength, okay, displacement over wavelength, that would mean this guy is one wavelength. This guy is one wavelength. So wavelength is in meters. This symbol over here is called lambda. Lambda. It's a lam and a da, right? Lambda. This is a Greek letter. Okay, so usually your wavelength is in nanometers or in micrometers. Please convert it to SI unit. What is it? It becomes times 10 to the minus 9 meters. And micro is times 10 to the minus 6 meters. If they give you micrometer, convert it to your meter. If they give you nanometer, convert it to your meter. Convert lah, buang lah dia punya N ni. Jadikan dia scientific notation. Okay, so that is the typical size for your wavelength. Okay, what else? Wavelength is also known as the distance between two successive points that behave identically. I mentioned to you before, when it starts to repeat itself, that is when you have reached one wavelength. Okay? Definition ni agak complicated nak hafal. Just remember when it starts to repeat itself, that is when you have one wavelength. One wavelength, one cycle, one period. Okay, sama. Okay, so frequency, we've seen this equation before, 1 over T and omega equals to 2 pi over T, 2 pi F. Naik muak dah dengar kan? Kalau tak ingat, tak tahulah, kena pakai sampai habis chapter ni. Okay? And then the speed of a particle. When we talk about the speed of a particle, we are actually talking about the motion up and down. How fast is it going there? How fast is it doing the oscillation up and down, up and down, up and down. That is the speed of the particle. It is instantaneous speed. It is called instantaneous speed. Nanti kalau ada soalan yang ada instantaneous speed pasal particle ni, I will include it in the lecture punya problem solving nanti. And then the speed is in meter per second. Sekejap
Ngantuk. Macam mana korang boleh survive? Kim.
Okay, so the speed of a particle is with respect to the y-axis. So this is y-axis lah sebab dia going up and down. Whereas the speed of the wave is with respect to the x-axis. Okay, so it's this one, the v to the right. This one is the up and down v. Okay, so it's different. The v particle is up and down. The v of the wave itself is to the right. Okay. Okay, so wave speed. Let's talk about wave speed now. The speed of a wave is dependent on the medium in which it is traveling. So what does that mean? Okay, so imagine that we have a cup of water. Okay, contoh, okay, cacat pula cawan ni. So I have light lah. I have light propagating, obviously. But when it reaches the water, it bends, right? Because why? The water is denser than air. Okay, sama juga situasi kat sini. It bends because the speed changes. So that is why they bend lah. Sama juga dekat wave. When we have a different medium, at first we were propagating in this medium and then we propagated into a different medium, the speed changes. Okay, so that is what it means. The speed of a wave is dependent on the medium in which it is traveling. Okay, here they said that in when the period is 2 seconds, okay, the period is 2 seconds, and your wavelength here is greater than this guy. This guy is small. The wavelength is small. Here the wavelength is big. Okay, let me write big here. And this guy is small wavelength sebab dia pendek Wavelength kan dalam meter. Kalau dia makin kecil, pendek lah. So this guy is big. When your lambda is big, your velocity is also big. When your lambda is small, your velocity is also small. Why? Because velocity is related to displacement over time. When your time is constant but your displacement is changing, your displacement is in meters, right? So if your lambda is big, which means that your V is also big. This is in meter, this is in second. This is in meter, this is in seconds. Okay, when your lambda is big, your V is also big. You are traveling faster. When you are traveling more distance, come faster. You are traveling more distance over time. When your lambda is small, your V is also small because you are traveling less distance over time. Okay, so that is just that. So from that we have.
Doktor.
Yeah.
Kan yang ni kan kita guna V. Ada untuk dia bergerak laju mana kan. And then kalau omega tu macam mana pula? I mean like V arah mana, omega arah mana? Kan ada beza ke?
V arah mana, omega arah mana? Omega.
Bukan ke V tu dalam dunia linear, omega tu dalam dunia putaran? Bukan macam tu?
Betul?
So ni kalau kita nak kira something yang bergerak linear, kalau kita pakai omega, kita kira untuk something yang bergerak circular motion lah. Maybe lah, I don't know. Betul tak tu?
Menjawab soalan tak Hakim?
Still tak faham.
Oh,
Does that mean kalau contohnya kalau pendulum ke contoh dia bergerak tu dan keluarkan wave, let's say for example contohnya pendulum tu dia bergerak on certain omega, keluarkan wave on certain velocity macam tu.
tak boleh.
Like okay, let's say contoh lain macam kita pukul gendang ke apa, so kalau tak boleh juga, I don't know.
Okay, tak apa. Okay,
Maybe wave memang tak boleh bergerak kot. Wave tak ada omega kot rasanya. Dia ada V je.
Dia ada omega. Kejap, nanti kita bagi tahu. Okay, so yang saya cerita ni.
Dr. Nat.
Yep.
Sorry to interrupt, Doctor. Kalau soalan pasal omega, won't they give us a hint about period or frequency first so that we just times 2 pi?
Yes, betul.
Bukan macam tu ke?
Selalunya macam tu. Okay, so now I'm going to continue. Okay, so here yang saya cakap pasal V ni is linear, betul. This is linear. But we know that wave has movement, right? It has movement, it moves forward, it also oscillates, which means that it has repetitive motion. And the equation to relate the repetitive motion with the linear part is this guy. Okay, remember frequency is 2 pi, omega equals 2 pi f. So frequency equals to omega over 2 pi. Right, so this is how you relate the velocity with omega. Lambda is in meters, frequency is in over seconds or hertz. Okay, so V is in meter per second. Okay, so ada linear part to it, ada the repetitive part to it, the oscillation part, and we also have to relate it by the lambda, the wavelength. Does that answer the question, Hakim?
Yes, Doctor. Thank you, Doctor.
Okay. Right, so this is a general equation that can be applied to all types of wave. Again, tadi kita cakap when lambda increases, V increases. Does that satisfy here? Yes, it satisfies this equation. Okay, so boleh pakai equation ni. Wah, bising budak ni. Okay. So now we are talking about, dah habis dah cerita pasal V. V equals to F lambda. That is your very, very, very important equation. Apa lagi equation yang kita dah belajar so far? Have we learned anything else apart from that? We learned about amplitude. We learned about lambda. Okay, so that is the equation. V equals to F lambda. Okay, so that's your first equation for this part. Okay, so wave propagation across a different medium. When a traveling wave reaches a boundary of different media. Part of it is reflected in the same medium. Okay, reflected maksudnya terpantul lah. Terpantul balik masuk dalam medium yang sama ataupun and part of it will be transmitted. Separuh lagi, bukan separuh lah. Some of it will travel ke dalam medium baru ni. Let's say this is medium A. Let's say this is medium B. So here, the wave was traveling like this. And then bila dia sampai dekat B, dia berubah. And then ada bukan separuh lah. Some of the energy from the wave terpantul ke bawah sini. Ni yang terpantul. Yang ni original. Yang ni yang transmitted. Okay, so ada 3 situasi. Satu original, satu transmitted, satu yang terpantul. So perbezaan kat sini ialah depending on the type of medium. Okay, let's see apa yang berlaku. Okay, saya pakai sini balik lah. I'm going to use this one as balik. Okay, so saya ada pulse. Pulse ni wave juga. When A is high, when A is low density compared to B, so B ni high density apa yang berlaku is pantulan tu akan terbalik. Tadi saya transmit macam ni. Let me use a different color. Tadi saya transmit warna oranye. Warna oranye ni, warna oranye. Okay, saya transmit warna oranye. Yang terpantul warna pink. Dia terbalik. It becomes inverse. Okay, kita cakap pasal reflect dulu. This is when my A is low density and my B is high density. Contohnya, this is air and this is the wall. Saya transmit wave, apa yang terpantul? Terbalik, inversely reflected. Now let's say A is high density, okay, and this guy is low density now. This guy is high, this guy is low. Apa yang berlaku? Pantulan dia akan pada sama direction dengan yang sebelum, yang original lah. So pantulan dia akan jadi macam ni. This is the pantulan. Dia akan bergerak ke kiri. Tadi saya punya original bergerak ke kanan. Pantulan dia akan bergerak ke kiri. Kita cakap pasal pantulan je baru So this happens when A is high density, contohnya dia wall, dan B is low density, contohnya air. Okay. So this is what happens. So what is the property of pantulan ni? The wave that is reflected maintains the same length, maintains the same frequency, maintains the same speed. Apa yang berubah? Shape je yang berubah. When does it become inverse? It becomes inverse when low to high. Okay, low to high. This is transmit. Nak cakap ni. Low to high density and it becomes normal. Dia jadi pantulan yang biasa when the medium is high to low. Okay, maksudnya yang ni lagi besar, lagi padat lah, lagi tumpat. Dia menjadi inverse kalau yang datang pantulan, dia terpantul daripada benda yang tumpat, dia jadi inverse. Okay, so apa properties reflected wave? Semua sama kecuali shape depending on the density of the medium. Kalau dia tanya, what is the properties of reflected wave? So you have to say it maintains the same length, it maintains the same frequency, it maintains the same speed. The shape is dependent on the density of the medium it is propagating in. Alright, so reflected high to low. Okay, let's see an example of this. Reflected from high density to low density. Apa yang berlaku? Dia akan reflect normally. So this is a rope. Rope is the medium A and B is this part. Bukan tiang. Sebenarnya kita reflect dekat udara. So ni tali and then ada ring and then baru ada tiang, right? So tali, udara, tiang. So apa yang berlaku kat sini? You are propagating from tali to udara. So this is high density to low density. That is why this example stands. Walaupun ada tiang ni confusing. Sebenarnya kita lalu dekat udara dulu, baru kita lalu dekat tiang. So, bila kita ada propagating pulse, this is our incident pulse. Pulse yang kita transmit. Dan kita lalu dekat sini, dia akan patah balik dalam keadaan shape yang sama. Shape yang sama. Everything else is maintained. Okay, so that is one from high to low. What about low to high? Dia akan jadi inverse. We already talked about this. Contohnya medium A is tali, medium B is wall. Yang ni lagi tumpat, wall lagi tumpat. So what happens when I libas tali macam tu, dia punya shape akan jadi inverse. Yang lain semua sama, maintain the same frequency, maintain the same speed and maintain the same, apa tadi? Satu. Wavelength. Okay, wavelength, speed, frequency. Sama. Wavelength, speed, frequency. Wavelength, speed, frequency. Okay. F lambda. Wavelength, speed, frequency. Maintain. Okay. So now kita nak cakap pasal properties of transmitted wave. So tadi kita cakap pasal yang terpantul, kan? Sekarang kita nak cakap apa yang berlaku dekat wave yang dapat travel melepasi boundary tu. This guy is called boundary. Hello. Selalu dia macam ni. Okay, this is your boundary. Apa itu boundary? Apa boundary lah? Tempat antara medium A dengan medium B lah. Okay, so this is medium A.
Sempadan.
Sempadan, thank you. Okay, sempadan antara medium A dengan medium B. Okay, so transmitted wave is apa yang apa wave yang melepasi sempadan tu ya. Separuh, bukan separuh. Some of it are reflected, some of it are transmitted into the new medium. So what are the properties of this transmitted wave? This is called transmitted wave. Okay, so it is reduced in amplitude, reduced in wavelength, reduced in speed, but maintains the same frequency. Frequency je yang sama, yang lain semua lain. Okay, so that is the properties. Frequency je sama. Okay, so saya akan stop dekat sini for your next lecture. Part ni tinggal pasal maths. Okay, so I know it's late and you guys, you know, I know how you feel about maths. Okay, so kita akan continue in next lecture. Okay, and I will combine that with problem solving sekali. So any questions about this lecture today? The lecture today. Is everyone okay?
Doktor nak tengok
Nak tengok slide mana?
yang
Doktor,
Ni,
low to high sekejap.
low to high. Macam ni lah.
Okay dah. Doktor.
Yes, Belle?
Doctor, but why does the wave become inverted from low to high, then high to low? Why does it like normal orientation?
I don't know. Honestly, I don't know. I haven't read into it. If you find out, you can let us know, Belle. Tapi sebenarnya saya tak tahu Bukan, I'm not being sarcastic. I really don't know.
So technically kita kena hafal lah, Doctor.
Yes.
Doctor, one more. What is an undamped oscillation?
What is undamped? Maksudnya dia tak damp lah.
Sorry, underdamped.
Oh,
not undamped.
underdamped. I don't remember the definition lah. Sekejap. Tengok balik buku. Is it in your module book? Tadi kan?
Yes, Doctor. 113.
Ada. 113. Okay, I can tell you right now that it's not going to come out in the exam. What you need to know is the difference between damped oscillation versus normal oscillation. Okay, sebab under damped,
Okay, thank you, Doctor.
it's like just definition je.
Kalau the motion to damp,
Mhm.
displacement kan decreases with time, but the decrease nilai dia berkurang tu tidak tetap kan?
Ulang balik, Meon.
Kan kalau damp harmonic motion kan senang kata pelembapan kan, benda ni kan pelembapan betul?
Betul?
Pelembapan menyebabkan satu-satu ayunan tu makin lama dia akan jadi stop, betul?
Betul?
So dia ada macam nilai tetap ke? Means dia akan berkurang setengah ataupun dia akan berkurang suku ataupun dia bergantung pada faktor I don't know, some maybe friction, maybe rintangan angin.
Betul. Dia akan berkurang ikut friction. Kalau friction tu tak berubah, dan patutnya pengurangan tu ada kadar dia lah.
Alright. So kalau saya kata yang menyebabkan pelembapan tu hanya friction, so pelembapan mengikut kadar friction tu lah.
Mengikut energy yang lost to friction. Boleh?
So dia kalau friction tu 10 Newton, so dia akan kurang 10 Newton.
Betul?
Thank you.
Okay. Any other questions? Is everyone okay? Okay, I'm going to stop sharing. Okay. Okay, that's it, guys. I'll see you on Thursday. Thursday. Okay. So take care. Don't forget to eat. Jangan stress sangat. Don't forget to revise for your physics. Okay. Okay, bye guys. Take care.
Thank you, Doktor. Bye, Doktor.
Thank you, Doktor.
Thank you, Doctor.
You're welcome.
Doktor.
Bye.
Doctor.